Good morning. This is just a short review, sort of a little extra video that I'm making to remind you a little bit about integration, which you're going to need for chapter 3 in our probability course. So let me just take over the screen now and start our discussion. Okay, so I want to first talk about improper integrals. And this is just a quick review of how one handles them. What's going to happen in probability theory is we're going to get integrals involving infinities. For example, we're going to have integrals of the following type, for example. Where a is some finite number, firstly. So the question is, how do you handle a problem like this? Well, the answer is, assuming this integral has a value, it converges. What we do is we replace the infinity by some number n, and we evaluate this as an ordinary integral. And we take the limit as n goes to infinity. For a simple example, consider the integral, say, from 1 to infinity of 1 over x squared dx. Well, so what I'm going to do is, first I'm going to rewrite this as the integral from 1 to n. Instead of x squared, I'll write this as x to the minus 2 dx. And this becomes, if I integrate this, increase the power by 1, divide by the new power from 1 to n. And this is just minus 1 over n between, minus 1 over x as x goes from 1 to n, or minus 1 over n plus 1. Now, to evaluate the actual integral, the integral which was from 1 to infinity of x to the minus 2 dx, I just take the limit as n goes to infinity of 1 minus 1 over n. And as n goes to infinity, 1 over n goes to 0, and this limit is 1. So I've just shown that the integral from 1 to infinity of 1 over x squared dx is equal to 1. By the way, I could do this a little shorter if we adopt the following convention. Suppose I actually wrote it this way. Okay, so I'm rewriting it. I'm actually rewriting the same steps as before. And suppose I kept in the infinity. Well, then this is minus 1 over x. So if I actually put in the infinity now, I would get the following. I get, firstly, this of course is minus 1 over x between 1 and infinity. If I actually put in the infinity, I get minus 1 over infinity plus 1. Now, by 1 over infinity, I really mean minus 1 over n, as I had before, and if I let n go infinity. But I could be a little sloppy and understanding that 1 over infinity is 0, and I can just write this answer as 1. Here's another example. Suppose let me just remind you that if I take the integral of e to the ax dx, where a is a constant, this is just 1 over a e to the ax. So in particular, if I gave you the integral from 0 to infinity of e to the minus 2x dx, well, if I do it the long way, what I'll do first is I'll look at the integral from 0 to n of e to the minus 2x dx. That's equal to minus 1/2 e to the minus 2x from 0 to n. That's equal to minus 1/2 times e to the minus 2n minus 1. Or if I now take the limit Well, let me just remind you that I could write this as 1 over e to the 2n minus 1. If I now take the limit as n goes to infinity of minus 1/2 1 over e to the 2n minus 1, in the bottom I get e to the infinity power, which is infinity. So 1 over, this is roughly 1 over infinity. And this answer, therefore, 1 over infinity is 0. So my answer here turns out to be just 1/2. Again, I could have been a little sloppier and not put it in the end if we understand what it means. That is, I could have written the integral from 0 to infinity of e to the minus 2x dx is minus 1/2 e to the minus 2x from 0 to infinity. Well, let me just rewrite it one more time. This would be e to the minus 2 times infinity minus 1, or minus 1/2 1 over e, or 2 times infinity is infinity. So this is 2 infinity, which is infinity, minus 1. E to the infinity power is infinity. 1 over infinity is 0. So this term is 0. And once again, I get the answer 1/2. Similarly, I can also have integrals like the following kind. Say the integral from minus infinity to, say, to minus 1 of 1 over x squared. Oh, I would do this problem exactly the same way. I'd say, okay, let's replace the minus infinity by n. We'll let n go to minus infinity. Then I would rewrite this as n goes to minus infinity of x to the minus 1 over minus 1 as we go from n to minus 1. So this is equal to the limit as n goes to minus infinity of, this would give me minus 1 over n plus 1. As n goes to minus infinity, 1 over minus infinity is still 0. This answer would be 1. And again, I could be sloppy and immediately write the following. The integral from minus infinity to minus 1 of x to the minus 2 dx is equal to minus 1 over x from minus infinity to minus 1. And now if I substitute, I would get 1 over infinity plus 1, because minus 1 over minus infinity is plus 1 over infinity. This, of course, is 0, this term. So again, I get 1. Okay, so if we can work out an integral like this and we actually get an answer, then we say the integral converges to that answer. Now, just an example, here's an integral that diverges. Suppose I had x squared dx. Well, if I integrate this, I would get x cubed over 3 between 1 and infinity. And if I just blindly plug in the infinity here, well, of course, this term will be infinite, and this answer is infinite, so this integral will converge. Okay, the last idea about these improper integrals that we're considering in this course is, what do I do if I have a problem like this? Integral from minus infinity to infinity of some function that I want to integrate like so. And the answer is, while you're tempted to be a little sloppy, the correct way to do this problem is break this integral up into 2 integrals. From minus infinity to 0, plus the integral, say, from 0 to infinity. I arbitrarily chose 0. You could choose any point in between minus infinity and infinity. Usually 0 is the best choice. It makes life most simple. Okay, now these are 2 problems I just showed you how to do. So if you wanted to do this problem, you work it out as above. And you see what happens is we go to minus infinity. So technically you would work this one out as, say, from, say, n to 0, and then let n approach minus infinity. And this one, you would work this out as, say, from 0 to m, I'll call it m, it should be a different number, and let m go to infinity. In order for the original integral to exist, both of these integrals have to exist. And we'll have some examples of this when it comes to analyzing probability functions. So basically, how do we handle a problem of this type? To be technical, what we do is we replace the infinity by some number n, and then we compute it. If this converges and we get a finite value, that will be the answer. Similarly, an integral of this type from minus infinity, say to a, I'll call it a, to say some number b of f of x dx. What I would do is I would replace this number by some other number, say m or n, doesn't make a difference what I call it. And I let m go to minus infinity. If each of these converges, then the respective integral converges. And lastly, if I have an integral from minus infinity to infinity of some function, I break this up into two integrals, choose some point in between. I usually choose 0. And now, if I call this result 1 and this result 2, now apply results 1 and 2. And that's how we do an improper integral. Okay, that's the first part of this. The last remark I want to make, or the second kind of example I want to consider, is for those of you who didn't take calculus 2, I just want to tell you about a very powerful method of integration called integration by parts. Now, we all remember the product rule. The product rule says the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. Okay, now let's reverse this. So if I reverse this, so if I integrate both sides, and I'm leaving out the arbitrary constants, I'll deal with those later. If I reverse this, then the integral of a derivative is back where you started, except perhaps an arbitrary constant. And this would give me u dv dx. I'm assuming, of course, both u and v are functions of x, plus the integral of v du dx dx. And by the way, I could just rewrite this as u times dv using differentials plus v times du. And now if I just transpose, I get the following silly formula. It looks like all I do is apply the product rule and reverse it. I get the formula u dv is equal to uv minus v du. This is the so-called integration by parts formula. Okay, now normally one uses integration by parts when one wants to integrate a product. For example, let me just remind you before I go any further, the integral of e to the ax dx, remember, is 1 over e to the ax, plus of course an arbitrary constant. So let's suppose I wanted to integrate x e to the 2x dx. So what I need to do is I need to identify one of these with u and the other one with v. And usually there's a choice, but if you make the wrong choice, you'll know you did so because you get a more complicated answer than you started with. So let's suppose in this problem, I choose u, identify u with x, and dv with e to the 2x dx. Then the derivative of u is 1. And if I integrate the expression, this expression, I get v is equal to 1/2 e to the 2x. Notice I'm leaving out the arbitrary constant. I'll deal with that at the end. So according to my formula, the integral x e to the 2x dx is equal to u times v minus v times, oh, I should say, by the way, du is 1 dx. So what do I have? I have x e to the 2x dx is 1/2 x e to the 2x minus 1/2 e to the 2x dx. And notice this is an integral I can now do. It's a simpler integral. If I made the wrong choice, for example, if I had called u e to the 2x and v x dx, I would have gotten an integral that was more complicated than what I started with. Okay, so let's continue. And now, e to the 2x, if I integrate that, I just get, again, 1/2 e to the 2x. And now that I'm done with all integrations, I'll add on the arbitrary constant. And I get as my result 1/2 x e to the 2x minus 1/4 e to the 2x plus the constant. So I was able to do an integration by parts here. That is, I broke it up into 2 different parts. And a problem that seemed to be harder to do really turned out to be very simple. Okay. I want to remark, by the way, that sometimes we have a definite integral that we do by parts. For example, u dv, the formula is almost the same, except it would turn out to be uv evaluated between a and b minus the integral of v du evaluated between a and b. Now, sometimes integration by parts has to be repeated. What do I mean? Well, let's look at a very similar example to one I did a minute ago. Suppose I have the problem x squared e to the 2x dx, and I wanted to compute this integral. Well, if I proceed as before, if I let u equal to x squared, then du is a derivative dx. If I let v equal e to the 2x dx, I'm sorry, if I let dv equal e to the 2x dx, then if I integrate this, I get v is equal to 1/2 e to the 2x. Again, I leave out all our arbitrary constants until the end. So now, according to the integration by parts formula, it's u times v. So if I call the integral I, so I don't have to write it again, this integral is equal to u times v minus v du. So I get 1/2 x squared e to the 2x minus 1/2. And now look what I got. I get, well, 2's cancel, so let me get rid of that. So I get minus just x e to the 2x dx. Now notice the resulting integral is of lower order than the original one I started with, which means I'm moving in the right direction. However, I just did this problem. The problem I did a minute ago was the integral of x e to the 2x. And the answer to this problem was, what was it, 1/2 x e to the 2x minus 1/4 e to the 2x. Where to go? So if I do this, and now I'll add on my arbitrary constant. Okay. So I now have the result of this problem. So notice here I actually have to do a double integration by parts. If I hadn't done the problem before, then I would have to do this as a separate problem. But I purposely rigged the problem where I did do it a moment ago, so I didn't have to do it again. Okay, so in general, here's an interesting thing. If you have a problem of the type, say p of x times some other function, say q of x dx. And suppose you can integrate q of x fairly easily. Then usually you will let dv equal to q of x dx, because this can always be differentiated. Differentiation is always easy to do. Now, in general, if we have an integral like this, and they both can be integrated and they both can be differentiated, well, which one do you do? Usually, if this is a polynomial, usually, but not always, you let u equal to p of x. Because ultimately, every time you do an integration by parts, you do a differentiation. So if it's a polynomial, after one differentiation, it's a polynomial of lower order. And ultimately, if you have to do repeated integration by parts, the problem becomes very simple. And let me illustrate. In fact, let me illustrate by making an observation. Notice in the problem I did a minute ago, the double integration by parts, I had an alternation of signs, plus, minus, plus, and okay. So in fact, let me show you how to abbreviate the integration by parts by doing the same problem again. So let's suppose I want to do this problem x squared e to the 2x dx. So I'm going to redo this problem, but a very clever way. So I'm going to give two columns. I'll call the derivative column, which is really the u term, and then I'll have the integral column, which I'll call the dv term. Okay, so I'm going to let u be x squared, and the dv I'm going to let be e to the 2x dx, but I won't write the dx. It's understood. Well, if I differentiate x squared, I get 2x. If I integrate e to the 2x, I get 1/2 e to the 2x. Now let me remark, if I stop right now, here's how I would read the answer. I put a plus sign here, and when I go across columns, I would integrate, and I would read the answer as x squared times 1/2 e to the 2x minus the integral of 2x times 1/2 e to the 2x dx. This is just a shortcut method. Now notice this is exactly the integral I had up here. There it is. That's if I stop, but suppose I don't stop. So let me erase this step. It'll be in the video. So let me get rid of this. And suppose I did it again. Well, the derivative of 2x is 2. And this integral would give me another 1/2. So I get 1/2 times 1/2, or 1/4 e to the 2x. And notice there's a 2 here. If I differentiate 2, I get a 0. So let's do it one more time until I get a 0. And if I integrate, this would give me 1/8 e to the 2x. Now, the interesting thing is, every time you do an integration by parts, the signs change. So we put a plus sign here, a minus sign here, a plus sign here, and across columns we integrate. But notice the integral is going to give me a 0 because I have a 0 here. So here's how I read my answer. I get x squared. So the integral I had before, will be x squared times 1/2 e to the 2x minus 2x times 1/4 e to the 2x plus 2 times 1/8 e to the 2x plus the integral involves a 0. I don't really care what this is. Doesn't matter. Plus my arbitrary constant. So I get as my answer 1/2 x squared e to the 2x minus 1/2 x e to the 2x plus 1/4 e to the 2x plus a constant, which is exactly the answer I had a minute ago. But notice this allows me, this method, which sometimes is called tabular integration or tabular integration by parts, enabled me to do the integration very, very quickly. By the way, sometimes there's an interesting trick. Suppose I wanted you to compute this integral, ln of x dx. Well, the trick is to think of this as being ln of x times 1 dx. And if I call this one u and this one dv, notice u is ln of x and dv is equal to 1 times dx. Then the derivative du turns out to be 1 over x, and v is equal to x, right? The integral of 1 is x. So u times v, if I call the integral I, u times v is x ln of x minus v times du. This integral of is just 1. So I is equal to x ln of x minus x plus an arbitrary constant. Or the integral of ln of x dx is equal to x ln of x minus x plus a constant. Okay, so here you have it. You have a quick review of improper integrals. And I snuck in along the way integration by parts. And I want you to realize that this method I just gave you of tabular integration really, really speeds up the process when you integrate by parts. Just one last example. Suppose you wanted to do x to the 4th, e to the minus 2, let's say make it e to the minus 3x this time, just to be different. E to the minus 3x dx. Well, if I take my derivative column and my integral column, I just want to show you I can do this problem real fast. Here's x to the 4th. Here's 1 second, let me just silence this. And here's e to the minus 3x. The first differentiation gives me 4x cubed. The first integration gives me minus 1/3 e to the minus 3x. The next one will give me 12x squared. This would give me 1/9 e to the minus 3x. Remember, every time I integrate, I bring down the factor. This gives me 24x. This gives me minus 1 over 27 e to the minus 3x. When do I stop? I stop when I get a 0 on the left. This gives me a 24. This gives me a 1 over 81, e to the minus 3x. This gives me a 0. This gives me minus 1 over 243, e to the minus 3x. And now I get this alternation of signs, plus, minus, plus, minus, plus, and of course the integral will be a minus sign, will be a 0. So I get as my answer x fourth times minus 1/3 e to the minus 3x plus 4x cubed. Now there's a minus sign, so I get a minus 1/9 e to the minus 3x plus 12x squared times minus 1 over 27 e to the minus 3x plus 24x minus 1 over 81 e to the minus 3x plus 24 minus 1 over 243 e to the minus 3x. And of course, my arbitrary constant. I can make this look a little prettier. I can take out e to the minus 3x for everything if I wanted to. Then I would get minus 1/3 x to the 4th minus 4/9 x cubed. 3 goes 4 plus 4x squared. 3 goes 9. 3 goes minus. 3 goes 8. 3 goes 27. X. 3 goes 8 plus 8. I'm sorry, there's a minus sign, isn't it? Minus, yeah, this one's a minus. Minus 3 goes 8, 3 goes 81, plus an arbitrary constant. Check my arithmetic here. I did it very quickly. This will be as far as I really want to go on this, but you now have a quick review, and I will post this for you, and you'll have it for your class. Thank you.